Let's jump right into today's explainer. We're looking at a pretty incredible story about the hidden traps of hardware testing. If you've ever dealt with electromagnetic compatibility or EMC testing, you know it's a make-or-break phase for any new product. But today, we're going to see exactly why taking the easy way out of an EMC problem can actually be the most dangerous move you can make.
Seriously, have you ever been in this exact situation? You implement a quick fix, you pat yourself on the back, and then boom, you realize you accidentally broke two completely unrelated things down the line. It's the ultimate hardware engineering nightmare, right? Well, today we're breaking down exactly how this happens, step by step, through a seriously fascinating real-world case study. So meet James. He's a super passionate hardware engineer working at this growing tech startup, and he walks confidently into the EMC testing lab. He's carrying his team's absolute pride and joy, their latest prototype. It's a sleek new device with a gorgeous integrated LCD display. They're essentially ready for a massive global launch. Literally, the only thing standing in their way is getting a clean bill of health from the lab. And honestly, the first few hours, absolute dream scenario. Hour 1, radiated emissions, totally clear. Hour 2, conducted emissions, perfect. By hour 3, they're running EFT, surge, and magnetic tests, and it is just a sea of green. James is feeling on top of the world. But then they hit hour 4, the dreaded ESD test. And man, this perfectly illustrates just how fast things can go sideways in hardware engineering. They're running the plus or minus 8 kilovolt contact discharge right onto the front panel, and disaster. The LCE glitches out completely, and the entire device just abruptly reboots. Just like that, his perfect testing streak is totally dead in the water. Now, here's where it gets really interesting, because his next move seems so incredibly logical. Frustrated, but staying focused, James pops open the prototype and spots the culprit right away. The LCD shielding just wasn't properly grounded. So he goes for a quick fix. He simply adds a short grounding wire going straight from the LCD frame to the main chassis. Puts it back together, they redo the ESD test, and it passes with flying colors. Problem solved. Or so he thought. James breathed this massive sigh of relief. He's eager to wrap things up and just get this product out the door. So he turns to the lab guys and says, "Awesome, it's fixed now. We don't need to repeat the other tests." But the seasoned lab engineer, who, let's be real, has probably seen this exact scenario play out 100 times, just smiles gently and insists, "Let's rerun the full suite, just to be sure." So, reluctantly, James agrees to the full retest. And he's about to learn a massive lesson here. Because relying on a quick grounding tweak without wanting to verify the rest of the system, that is a classic hardware engineering trap. It's a pitfall we see all the time in product development. And sure enough, when those retests start up, they get hit with some huge surprises. Tests that had passed perfectly just a few hours ago were now failing. Burst immunity fails, causing the CPU to absolutely glitch out under stress. And it gets worse. Radiated emissions fails completely because this brand new radiation spike suddenly pops up right around 120 megahertz. So this one simple fix literally just created two brand new major failures. To understand exactly why this happened, we really need to talk about the concept of an EMC trade-off. This is basically a scenario where altering a system's ground reference, or changing up its current paths to fix one specific issue, inadvertently opens up brand new vulnerabilities somewhere else. That tiny, innocent-looking grounding wire James added, it fundamentally changed the system's entire ground reference. Looking at the whole picture, you can really see the domino effect. That exact same quick fix that saved the device from the ESD strike became the very pathway that triggered that 120 megahertz radiation spike. It essentially turned into a little antenna. And not only that, it opened up a brand new route for burst interference to punch right through to the previously secure CPU. He fixed one problem, sure, but he traded it for two more. So, realizing the mistake, it was time to fix the fix, and this time, do it the right way. Instead of just slapping another Band-Aid on it and crossing their fingers, James and the EMC lab team actually collaborated. They completely redesigned the device's grounding approach from the ground up. The difference between these two approaches is just night and day. They moved completely away from that chaotic single wire that left the ground reference unchecked and the current paths completely altered. Instead, they went with a highly controlled architecture. The proper redesign used a much shorter shielded path, proper dedicated electrical filtering, and way more strategic internal cable routing. They systematically apply these careful tweaks, step by step, ensuring every single variable was accounted for.
First, they implement the shorter shielded grounding path. Then, they add the proper electrical filtering. Next, they secure those internal cables. And then comes the most important part, step 4. They execute a full suite retest from scratch before they even think about calling it finished. And the results of doing it right absolutely speak for themselves. The device goes back into the chamber and clears every single test with 0 glitches. ISED? Passed. Burst immunity? Passed. Radiated emissions? Passed. The overall status was finally clean, consistent, and truly production-ready. James's team was finally able to launch their product globally with total confidence, knowing there'd be no hidden surprises waiting for them in the field. The real lesson James took away from this is completely invaluable. Always, always retest. Repeating all of your tests after putting in any kind of fix isn't a waste of time at all. It is an absolute necessity if you want to prevent a cascading domino effect of failures. EMC issues love to come in chains, and fixing one link can so easily break another if you're not looking at the big picture. Ultimately, this whole story highlights a fundamental truth about hardware design. Even the smallest hardware change, especially when we're talking about grounding, can affect multiple EMC domains all at once. Look, a lot of engineers make this mistake early on, but the true pros, they learn from it. They never underestimate the widespread impact of what looks like a tiny, insignificant alteration. So, as we wrap up today's explainer, I really want you to think about this before you launch your next big prototype. Ask yourself, is your latest quick fix a true, comprehensively tested solution? Or is it actually just the beginning of a whole new chain of hidden problems waiting to bite you in the field? Take a page out of James's book. Design properly and always, always retest. Thanks for hanging out with me for this deep dive, and keep building with confidence.